Добрый день, меня зовут Nicole. Я говорю по-русски не очень хорошо. So unfortunately, that's all the Russian I know. But I tried, right? This is my first time in Moscow. And for the English speakers out there, my name is Nicole van der Hoeven. I work at Tricentis Flood, and I am Filipino, Australian, and Dutch. So before we start, I want to mention this thing, Slido, that was mentioned earlier, but nobody seems to be using. If you do want to use it, you can go to slido.com, put in TestCon 2019, and this is Hall 3. Or you can just ask questions later. Oh, there's the gong. That's when I should start. Okay. So I'm here today to talk about dismantling cognitive biases, particularly as they relate to performance testing. But what's a cognitive bias anyway? So what if I told you that you read the first line wrong? What's going on in our minds? Is it just an optical illusion? Because when we look at this slide and our brains immediately jump to the conclusion that it should say, what if I told you? Instead of sounding out each word one by one and seeing that there's a typo, what's going on in our heads when that happens? And what happens when we make those simple mistakes when we're testing? So today I'm going to talk about what cognitive biases are, and I'll go into a little bit more detail as to how we actually get to that point where we're heavily biased. And then I'm going to talk about what they have to do with performance testing and how cognitive biases can actually affect your performance testing results. And lastly, of course, I'm going to talk about how we can keep from falling into these traps of thinking. So back to what a cognitive bias is. This is a pretty highfalutin definition from Wikipedia. That's where I do my research. But generally, a cognitive bias is a mental shortcut that we rely on when we're making decisions rather than by tackling it logically. So, see, our minds are wonderful things. And when we test software or build software, there's a lot that's going on in the backgrounds of our minds. We are, in the background, processing intuitions and impressions, and these things happen instantaneously, even without us really thinking about it. So there's an author called Daniel Kahneman, and he wrote a book called Thinking Fast and Slow, and he calls this system of thought System 1, but I just like to call it fast thinking because that's what it is. It's fast, it's instinctive, and it happens without us saying that we need to actually solve a problem. So this is an example of when your fast thinking would kick in. See, when you look at this slide, even before I've asked you what is 2 plus 2, you probably already have the number 4 in your head, or 4, is that right? And that's fast thinking at work, because you haven't even been asked the question and you already have the answer in your head. That's pretty amazing when you think about it. And then there's slow thinking. See, slow thinking is the system of thinking that kicks in when we're presented with a problem that's just difficult enough to require a little bit more concentration and usually a bit more time, and that's why I call it slow thinking. It is really good, though, at systematic decisions where you really need to go line by line. And an example of this is this problem, 8 times 256. Now, if you're a normal person, this is not something that you're going to be able to answer right away. You are going to have to put some thought into it or whip out a calculator. But since this is an IT crowd, maybe there's a chance that some of you have developed a mental shortcut for this. Maybe the 256 immediately brings to your mind 256 megabytes, for instance, and you know that the answer should be 2 gigabytes, so 2048. So this is an example of how the same problem can present itself differently to 2 different people. And this is an optical illusion, but it's also a cognitive bias. See, I'll tell you right now that this is not an animation, it's not a GIF, it's just a flat image. And your slow thinking will kick in now, and you'll believe me, but your fast thinking might still look at it and think that the pips are moving. I know that when I look at it, I still think it's moving. But why are we so eager to believe our fast thinking over our slow thinking, even when we know logically that that's what we should believe? And this is the Muller-Lewis illusion. You probably have already seen this before. And if so, then you know that these two lines actually have the same length, except they're framed by different arrowheads. And that one difference changes it completely for us. For some reason, fast thinking still says that it's the second line that's longer, when it's really not. So what does this have to do with performance testing? It turns out quite a lot, because, see, there are a lot of managers or just a lot of people who maybe don't know so much about performance testing, and they think that what I do is in sort of a black box, and I do some sort of mysterious magic in there, and out the other side comes, hopefully, a performance application. And it's not actually a mystery. It couldn't be farther from the truth, because if there's something that a performance tester has to deal a lot with, it's data. This is something that I see every day. There's hundreds of megabytes of logs that you sometimes have to look through. And it's a good example of how slow thinking can quickly get overloaded, because slow thinking would process this line by line. There's no other way to do it. And you don't really give your fast thinking a chance to think about what you're going to do. But if you are experienced enough, how about searching? Because you do need to know the keyword, but if you are experienced enough, you may want to do that. And if you did, maybe you'd think to search for crit, which is on the last line of these logs. But it's still not something that you would know to look for right away. You couldn't look at that and know it's on the last line instinctively. And this is why tooling, especially in performance testing, is so important, because on the left side of the screen are the same logs that I showed you earlier, and they're still just as incomprehensible as they were before. But on the right side, there's a much friendlier message. So it actually says here that there's no space left on the device. We know instinctively that that can't be a good thing. So slow thinking doesn't need to kick in here. Fast thinking knows what's wrong. And this is a graph of CPU idle. Fast thinking might immediately draw our attention to that gradual decrease, because it's the most dramatic. So when we see that decrease, that's what we choose to focus on. But is that really where we would start our investigation when you're trying to figure out what's wrong? Slow thinking might kick in here, and you might think, well, what about that part at the beginning? Because you can see that sort of zigzaggy behavior. That's not something that you want to see. But too many people will just focus on fast thinking, on that decline, when actually the problem occurred much earlier. So another problem that I see a lot of in performance testing in particular is the anchoring effect, which is the bias that occurs when you rely too heavily on an initial piece of information, usually a number, even when that number is completely irrelevant. I really love this story of an experiment that I read, and it's about these German judges. They were all given this identical case study of a fictional shoplifter. They then had to roll a die, one of these things, and then immediately say how many months they would give that woman in prison. What they didn't know, what the judges had no idea about, was that the dice were weighted. So there really were only two possible options. One is a 3 and one is a 9. So they're on the opposite ends of the spectrum. What they found out is pretty mind-blowing, because the judges that rolled a 3 awarded that woman 4 months in prison, and those that rolled a 9 awarded her 8. Now you might be thinking, You wouldn't do that. You wouldn't let your decisions be influenced by something so arbitrary. But these judges had 15 years of experience. They were not new to the bench. So what's going on here? I think that it's just part of human nature to fall for these biases. So what if that number wasn't so arbitrary? What if it's not just a roll of a die? What if it has just enough to do with what your decision has to do with, that you actually think maybe there's a legitimate reason why you should use it? And I think non-functional requirements, or NFRs, is actually a really good place to see this. Because one of the most common non-functional requirements for performance testing is one that says this page should load in this case, 4.6 seconds. But where did you get that 4.6 seconds? Sometimes it's just finger in the air, someone just guessed. What if you try to put a little bit more thought into it, and you ask maybe the owner of a certain component that's part of that page, and he says it's 4 seconds that you should expect as a response time. So maybe you pad it out a little bit and say 4.6. Normally they choose large round numbers, but sometimes they don't. Not only can the NFR be influenced by these anchors, these potentially irrelevant, illogical numbers, but the NFRs can also be anchors in themselves, because once you've set that 4.6 seconds, are you really going to still continue testing the application if the response time is 4.5 seconds? Because for most people, the answer is no. And sometimes that's the wrong decision. Just because it meets that requirement doesn't mean nothing will go wrong and there aren't easy wins that you can still eke out of that sprint. And one of the problems with just focusing on a number is normally you focus on the average. And the average is pretty average. It's not really that good a metric for being able to tell you about the distribution of a set of data. So a lot of people actually use the 95th percentile instead. For instance, if you have a 95th percentile of 8 seconds, then that means that 95% of the transactions have a response time of 8 seconds or less. But what about that 5%? I mean, are we talking 10 seconds here? Are we talking 20? That could matter. That might be something you want to look into. But just focusing on that number isn't giving you the full picture. And another thing that I see a lot in performance testing is when we just chase symptoms. When the question is asked, why did the application go down? So worst case scenario. People say, oh, the CPU was too high. And then they stop there. But that's just the beginning. You should ask yourself, why was the CPU so high? Why was the response time so high? Those are things that are symptoms. They are not the root cause. And if you don't address it, it's just going to happen again. Just another way, another illustration of how we as humans just stop at the symptom rather than going further. So I'm going to actually share a slightly embarrassing production outage that we personally experienced. And in order to do that, I'm going to give you a little bit of context about what we do. I'm part of a team at Tricentis called Flood. And Flood is a cloud-based distributed load testing platform. What we do is we allow users to upload their test scripts from open source tools. We then take those test scripts and provision as many machines in the cloud as they want. And that enables them to ramp up to sometimes millions of users per second, all in our platform. So this is a basic diagram of Flood's architecture. It's not so important to really understand exactly what each part does. What I want you to pay special attention to is how the test results go through the system. So those gray blocks are actually machines in the cloud, in AWS or Azure. So each of those machines is running a performance test. And that performance test is generating results. Things like response time and number of users, the number of past transactions, that kind of thing. And all of those get pushed to microservices behind elastic load balancing in the cloud. They then get put into their own queue, which is backed by Redis, and then pushed to third-party servers, which process that data before putting them into our relational and time series databases. At the end of all of that is a dashboard that customers can see results in real time. And that's the dashboard that failed. This is what it looks like. Fast thinking really has a lot to work with here. You know that this test didn't go that well, but where would you actually start your investigation? There's so much to look at with fast thinking. It could look at the number of users, which in this case goes up to 15 million users towards the end of the test. There's response times, there's the throughput, the error rate, there's the individual transactions, number of passed and failed. There's a lot. But slow thinking might actually give you better clues here. Slow thinking might tell you to focus in the beginning, when you see that green line, which is throughput, the transaction rate, increases at the same time that the error rate increases. This is not a good sign. And everything after that is actually just noise. There was something not right in the test, in the application at this point. So there are 3 players in this story. There's me, I'm Nicole. I am based in the Netherlands, and I'm part of the support team. And that means that we help customers with troubleshooting their load testing scripts. We also help them analyze their results, and we provide recommendations as to how to proceed with their load tests. We're also all performance tests on the support team. The next one is Will. He is a DevOps engineer. So he's responsible for basically making sure that all our architecture, all our systems are running smoothly. He's based in Australia, and he was up late at the time that this happened. And the last person is Tim. He is our fearless leader. He is the co-founder of Flood, and at the time that this happened, he had just stepped off the plane from Austria back in Australia, so he was completely jet-lagged, but still on call for escalations. It all started with one customer who said that the real-time dashboard wasn't so real-time, which is not a good thing. So I thought that it had something to do with her account, but then more customers started writing in, and I knew that there was something wrong. Unfortunately, I work at a different time zone to most of the team, so there was only one person online. And that was Will, because he tends to be up late. Also, he had just come back from being on leave, so perhaps he was still used to staying up late. So I tell him that I'm seeing some worrying symptoms. I see that the queue depth is increasing in one of these servers that we have, which is why the results aren't getting processed in time, but some results are. He doesn't really know what to do here, and I remember that the month before, or something like that, I saw the same symptoms in another incident, but Will was away at the time, so he has no idea what I'm talking about. And that's me falling for the availability bias, which is a tendency to make decisions based on the most immediate, sometimes the most recent incident that comes to your mind. When I say, looks like what happened last time, that shouldn't be the end. That shouldn't be a reason for me to jump to the conclusion that the root causes were the same. That's a place for investigation to start, not end. But I'm the one dealing with the customers. So they're writing in, they're obviously unhappy, understandably so. They're pretty much running their tests blind, which is not what we want to happen. And I'm the one that's telling them, yeah, we know there's a problem, we're looking into it, but unfortunately, we don't really have a fix yet. So I take things into my own hands. I actually look at the postmortem that Tim did for the last production incident. A postmortem is basically a review for production incidents so that we can decide what we did wrong, what we did right, what we could have done in the future. And because I'm under pressure from customers, I look at what he did last time, which was restart these two services, drain and pipe, and I ask Will, pretty much tell him nicely, to restart it. And he does. Because he's fallen for the authority bias. And the authority bias is the tendency to place greater importance on an authority figure's opinion. Now, I'm a performance tester telling a DevOps engineer to restart services. I'm not the authority, but I mentioned Tim, which is the magic word because not only is he our co-founder, he's our manager. So he does what I ask. And initially, I actually think that it helps. I think that I see the queue depth decreasing slightly, maybe a little bit of a dip. But that's the problem with real-time graphs. Just because they're real-time doesn't mean they're not on a delay. And that's actually confirmed when Will sees these logs, these error logs showing up. There's a lot of them that's in the logs, and we have no idea what that means. It says cardinality limit exceeded. Since we have no idea, we call in the big guns. I make the late night call to Tim, who logs on bleary-eyed and jet-lagged, to tell us that that error is actually expected. So then he asks, what other errors do you see in the logs? And this is the only time that Will actually gives us this error, which is still a lot of nonsense. We're really stressed. We're really missing a lot of things here. And in fact, we should have been able to tell from this slide what the problem was. And if you can tell from this slide, then you did much better than we did. But I will get to that later. So then Tim starts to form his own theory. He thinks that it has something to do with the number of unique labels in people's load testing scripts. Again, not so important to understand what exactly that means. What's important here is that he has a theory, but it's not quite adding up and making sense in conjunction with the data. And you can see this when he says, the test might have slammed it. There's a hint of indecision because even he knows it doesn't quite fit. And this is the confirmation bias because he's not actually looking at what happened. He's looking to get the data to fit his theory. And this is someone with a lot of experience. You don't get to be the co-founder of a service like this for nothing. And he still fell for it. Will actually sees that far from decreasing, which is what I thought earlier, the queue depth has increased far beyond the point at which we restarted the services. So it's clearly not working. And here the customers again, asking me again, can you give me an update? And I still have nothing to tell them. This has been several hours now, and we're really still trying to come up with the root cause. We're ruling a few things out, but we're still not there. Now Tim is starting to think that maybe there's something wrong with the database because he notices that it's run out of connections, which Will thinks shouldn't happen because we should have enough capacity for that. Under pressure, they decide to redeploy one of the services, thinking that maybe there's a problem with the service itself. Oh, also, you can see that he says, theory is, and that's when you know you're in trouble, when you say the words in theory in production. So they redeploy the service, but it doesn't really help. And what's weird is we're still seeing these database connections that haven't been released. And this is database connections that were created by containers that were removed. So we're not sure why that's happening. It really shouldn't be. But there's just so many things that are not adding up. Finally, Tim figures out, using this chart, this graph, that the problem was that there were 8 containers running on one host. That's 7 more than we thought was possible and we would ever have expected. Of course, we don't have an alert for that. We have alerts for other things, but not that. And we also didn't have this graph. Let me tell you, we do now. So remember this slide when Tim had first logged on and asked Will for extra information? It was staring at us right in the face. It said DB availcons is 0. That doesn't even require that much experience to diagnose. That would have been a huge, huge clue. But because of this general production outage and the pressure from it, we all collectively missed it. And that's inattentional blindness, when you completely miss something that was right there and was extremely simple to see. So at this point, this had been going on for 7 hours on and off. I mentioned 4 cognitive biases that we came across in this production incident, and just those 4 led to 5 extra hours of an outage. We should have diagnosed it at 2 hours. So that's why it's important to think about how we can avoid biases and improve your performance testing. But maybe we should practice what we've learned here. Just because it's on the slide doesn't mean we have to do it. That's authority bias. So how about we ask ourselves what we should do about biases? Because biases are there for a reason. Remember when I was talking about those NFRs and how focusing on a number can be detrimental because you focus on that at the expense of your performance test or your application performance? Does that mean that we just shouldn't have NFRs altogether? Of course not, because NFRs give us a really good way of getting on the same page. It's a list of things that we're aiming to do with our testing. It gets all of the shareholders on the same page, and it gives us a good way to determine whether our tests have passed or failed. So clearly, just getting rid of it isn't a solution, at least not a good one. And similarly, if an animal runs towards you with its teeth bared, ready to pounce, you're not going to stop and sit back and think, let me analyze your behavior. Fast thinking and evolution, millennia of evolution, actually primes us to either fight or take flight. And that's because we know from experience that that's prudent. And what about that availability bias? Clearly it was illogical for me to jump to the conclusion that the 2 production incidents had the same root cause. But what if I'd been right? That would have saved a lot of time. Or what if I'd been wrong, but restarting that service for one reason or another actually helped the situation? Maybe it wouldn't have solved the issue, but it could have actually meant that customers were still able to log on and see their results, at least until Tim woke up and actually solved the issue. And what about Will's authority bias? Tim is our manager for a reason. He knows more about Flood's architecture, more than almost anyone on the team. So doing what he's done can sometimes be a smart move, but also, since he's our manager, it can also be a great career decision. So maybe what we should do is identify which system of thought is actually appropriate for that situation. If a situation is time sensitive, that's a good decision to consider fast thinking. If you choose slow thinking, which takes a long time, sometimes not having a decision right away is a decision. So what are the potential effects of that indecision? And if you choose fast thinking, what if you jump to a conclusion and roll out a fix and that fix is wrong? Basically what it comes down to is, can we afford to be wrong? Or is it something that we can try, and if it fails, it doesn't really affect anything? One situation that fast thinking really excels at is social situations. See, slow thinking is good at systematic, logical sets of rules, and human beings are nothing but chaos. Things like body language and tone, sarcasm, those are things that you really can't logically analyze. You instinctively process that with your fast thinking. In this picture, you can see that the man in the foreground is focusing intensely on something, and that intense focus is really reminiscent of slow thinking, which has like a tunnel-like focus, a laser-like focus, because you need all of your attention to concentrate on the problem at hand. But it also means that he's missing completely what the facial expressions of the two people in the background are saying. They've started to raise an objection, but he's missing it. I think that context matters. It's important to the story to realize that I was dealing with customers, Tim was jet lagged, and Will had just come back from leave and was working late. See, all of that meant that we prioritized fast thinking, something that we may not normally have done if we were thinking logically and at our best. So maybe what we can do is use these two ways of thinking in tandem. That's how they're meant to be used. So you can use fast thinking to say, have I seen this pattern before, and can I apply it in this situation? And temper it with slow thinking and say, have I missed something? Is there something else that could be causing the same issue? They're really meant to be used together. Fast thinking's instinctive reflexes, lightning quick reflexes and impressions, and slow thinking's more systematic, rigorous way of thinking. They're really best together. In this incident, I talked about just 4 cognitive biases, and really they contributed to a big part of the production incident. It was 5 more hours of a production outage. So maybe we just assume that we're biased, because these are just 4, but this is a full list of cognitive biases that I found. Probably there are more that I didn't find. So you could actually go through each of these and say, am I falling for this, am I falling for that? Or maybe just assume that you are biased and everybody around you is biased, and get into the habit of questioning yourself and everybody around you. Like, for example, with the anchoring bias, if you're worried about that number meaning too much to your team and yourself, maybe visualize it. Every time you see a number, visualize it, because the same numbers, the same mean and standard deviation, can lead to completely different graphs. And those graphs matter when it comes to application performance. And all measurements are wrong. Normally, we're performance testing not in production, but on a test environment. But is that test environment production-like? Is that test code production-like? Is that the build that's going to be released into production? What about your workload models? Maybe you thought that there was a page that nobody will go to, but it turns out in production that they do. It could be your script that's wrong. And even if all of these things are identical, it still doesn't mean that you can look at your performance test results and know with 100% certainty that that's what you're going to see in production. There's only one truly production-like environment, and that's production. It's so much better when you see a scatter plot. Rather than just the numbers, you can see that the average is 4.4 seconds, 95th percentile of 11.3, but you can see the outliers, you can see where all the transactions fall. And this is why I love raw scatter plots so much. I also like frequency distributions because you see not just the average 75th percentile and 95th percentile, but you can see that this test has quite a long tail, which means that even though the average is closer to 5 seconds, there are likely some users who are getting some seriously bad response times. Depending on the application, that could be a problem. And this isn't showing up too well, but it's basically a heat map. And the darker areas are showing higher concentrations of transactions. So that means that there are a lot of transactions that show that response time. And it lets you see outliers as well. I really love this slide because it talks about one thing that doesn't get mentioned when we're analyzing data, and that's granularity. See, all three of these graphs actually show part of the same data. The first slide, this is, by the way, CPU utilization. The first graph is showing it where 1 point is 5 minutes, so a relatively short time period, and it's showing that it's 40%. In the second graph, 1 point is now 1 day, and that 40% is now 16%. And the third graph exaggerates that effect even more because now 1 point is 1 week, and that 40% is now 8%, which is pretty significant. And that's the danger in looking at just 8% and not stopping to question how did you actually get to that number? What calculations went into that? And let's not forget the graph that initially caused him to say that this was the issue. Another thing you can do is try to be the wolf instead of just being a sheep all the time. Question yourself and everybody around you. And of course, with the availability bias, bring in slow thinking and ask yourself, what else could have gone wrong? With the confirmation bias that Tim fell for, focus less on being right and make it a little bit more exploratory. Now, with the inattentional blindness, what if you were testing the Titanic? You could choose to focus on the passing unit tests, because obviously there were some. Or you could actually look up and see that there was a big bloody iceberg that tore a hole in the hull of the ship. Take some time away from the problem, and when you come back to it, you'll come back to it with fresh eyes. You can also develop expert intuition by using your fast thinking more and more in different situations, and eventually it'll get to where slow thinking is in terms of accuracy. And seeking independent sources of data is a good thing because you can't really shoehorn all of that data into what you think has happened in the situation, and also independent sources of opinions within the team. I didn't actually ask Will what he thought, but I should have. Maybe if I had said, what do you think? Here are the facts. Maybe that would have been a cue for him to use slow thinking instead of fast. So here are the things that I think you should do about cognitive biases. First, you can identify whether fast or slow is appropriate. Secondly, use both of them if you can. Thirdly, you can just assume that you're biased and question everything, visualize any number. Develop expert intuition by just honing your craft. And lastly, seek independent sources of data and of opinions within your team. If you do all of these things, then I can't guarantee your performance testing will go completely smoothly, but I can guarantee it's going to be a little bit less mysterious and a lot more methodical. And if you forget everything, remember this one thing: question everything, especially yourself. So I'm going to, do we have time for questions? What she said. Okay, let me check Slido here. What's an example of another bias? Can you see this? Yes. That you didn't mention that you see a lot in testing. Okay, I saw one recently that I really like. It's called the IKEA effect. And that's what happens when you assign greater importance, significance, or you just overestimate something you built yourself. Because I've built all those things from IKEA, and that shelf that's a little bit crooked, I'll forgive because I made it. And sometimes we can be like that when it's software that we've built. We don't really analyze it critically. I don't think I can mark this as answered. Thanks, everybody.